When we make measurements, we never get exactly the right value. We've always got some noise associated with those measurements. And that noise will usually be distributed around a mean value that should be a pretty good measurement. And that distribution is often a centrally biased distribution, a centrally weighted distribution, and it usually looks a lot like a Gaussian normal distribution. So for that reason, we want to find out a little bit more about what a Gaussian normal distribution looks like and what its properties are. So a Gaussian normal distribution, or is often called a normal distribution or a normal error function, it's the least biased assumption you can make if all that you know about a set of data is its mean and its standard deviation. So it's also the distribution that you'll get if you combine a whole lot of random influences together. So if you roll a whole lot of dice, the results will come up looking a lot like a normal distribution. So throughout all of our work, we're going to always assume that our noise is Gaussian distributed. Now, if we knew something different, then we might be able to make some sense out of that knowledge. So I'm just updating this Python notebook as we go along to correct some of my typos. And you can follow along in the Python notebook called Gaussian Normal Distribution Basics so that you can try out some of this code yourself. So we're going to explore a little bit about Gaussian normal distributions. First thing we're going to do in this cell is import a bunch of stuff that we'll need in order to do our calculations. So running that makes sense. No interesting output. Now, what does the distribution look like for our Gaussian normal distribution? Well, we can plot it with a mean of 0 and a standard deviation of 1 to find out what the shape looks like, and that's what we're doing down here. I'm taking a linear space between -3 and 4 of 1,000 points, just to have something to plot over, and then I'm plotting this norm.pdf function over x, over that space, with a mean of 0 and a standard deviation of 1. So this is just calculating a whole lot of values, and then I'm going to plot those values and see what comes out. So if I run that, this is the plot I get. I get that shape there, and it should be a fairly familiar looking shape. It's a distribution you've seen fairly often. So looking up here, a couple of things to notice. One is the probability of any one sample lying between plus or minus 1 standard deviation, that is between -1 and 1, if our standard deviation is 1. The probability of it fitting in that region, 68%. Plus or minus 2 standard deviations, out to here at 2 and out to here at -2. That area in there, that accounts for 95% of the probability. And 3 standard deviations, out to here and out to here, that covers 99% of the probability. So those are some important numbers to at least keep in mind. About 2/3, 95%, and 99%. Now, the PDF function, this thing that we've plotted, gives us probability density. And probability density is defined as the probability per unit change in the independent variable. So that the integral of that probability density function from one value to another is the probability of a sample lying between those two values. So if I took the integral between -2 and -1 of this PDF function, then I'd have the area under the curve in this region, and that would be the probability of getting a sample in between -2 and -1. Not very big compared to the probability of all the other possibilities. So that's the notion, the idea of a probability density function. And another important thing to keep in mind about this Gaussian normal distribution is that even if we had a different mean and a different standard deviation, if we did this plot, it would look exactly the same, except for a change in the numbers on the axes. So instead of being 0 here, it might be 22.7. And instead of being 21.7 and 23.7, correspondingly, these might be stretched out or compressed a little bit, depending on what the standard deviation was. But the shape, exactly the same. So everything that we do with a normal distribution that's distributed with a mean of 0 and a standard deviation of 1, we can translate that into exactly the same things with different mean and standard deviation. Now, one of the things that we imported way up here was this SciPy stats library, and we imported just a small chunk of it called norm. Norm is a part of the library that's good for normal distributions, and we've used one of those functions already. Norm.pdf is what got us our PDF. So let's see if we can get some useful answers out of these functions. We might ask the question, what's the probability that a sample will be less than 1? So if the value here was 1, then the integral under this curve all the way back out to as far as we can go would be the probability of having a sample turn up to be less than 1. So the integral under the PDF curve is the cumulative density function, that CDF function. So we could find out what the CDF was when we got to 1, and then we'd subtract 0 because it was way over here. And so we could use this norm CDF function, run that, and we get 0.84. So less than 1, this whole region over here, it integrates out to about 84%. And that intuitively matches up with what we see from the shape. Now, if we wanted to illustrate that process, we could go down here. We could calculate the PDF like we did before. That's the blue line here. We could calculate the CDF, which we didn't do before. That's the orange line here. It's the integral of the PDF. So if we integrate the PDF from way over here all the way up to 1, then the CDF is, there's about our 84%. So along the way to making this illustration, we can see a little bit more about how some of these plot functions work. We can plot f and g, that's just drawing the blue line and the orange line. Then I'm taking another x range and I'm making it a linear space that only goes up to 1. And I'm getting another f set of values that only goes up to 1. So that's just that collection of data that goes all the way up to here to 1 and then stops. The reason I got that is so that I could draw this filled plot along the region from x going from -3 up to 1 for stuff that lies in between a value of 0 and that value of f going up to 1 here, and that fill between function fills in that space there just to indicate that we've done the integration. I've also done a plot here with these x values, 1, 1, and -3, and these y values, 0, the CDF value, and the CDF value again, just to put this green line on here so that I could show it to you. So this shows you a little bit more about what you can do with plotting. Now there are other kinds of questions we could ask. For example, how large is the region containing 95% of the probability if a distribution has a mean of 192 and a standard deviation of 10? Well, remember that 95% of the probability lies in between about plus or minus 2 standard deviations. So 192 minus 10 would be 182. Minus 2 standard deviations would be 172. And plus 2 standard deviations would be 212. So if I use this norm interval function to find for 95% probability with a mean of 192 and a standard deviation of 10, what are the bounds of that interval? And I print it out, well, I get 172.4 and 211.6. So my two standard deviations thing that's at 172 and 212, that's a little bit of approximation. It's not exactly 95%, but it's pretty darn close. So if we look 172, 212, this region in here of this Gaussian distribution accounts for 95% of the total distribution. And notice the shape is exactly the same as it was when we had a mean of 0 and a standard deviation of 1. We're just getting different numbers on the axes now. So I've figured out what that region would be if I wanted 95%. If I wanted to know 92%, I could just do it all over again. And I'll find a little tighter region. If I wanted to know 50%, I can do it all over again. And I get a considerably tighter region, less than 1 standard deviation away, down about 7 and up about 7. So about 7/10 of a standard deviation away for 50%, because 1 standard deviation would give us 68%. So that makes sense. So we can use this norm interval function to find out the region around the mean that contains a certain percentage. If we wanted to find out something a little more involved, say we weren't interested in something symmetric about the mean, we might ask a question like, if temperature readings were normally distributed with a mean of 24.5 degrees Celsius and a standard deviation of 0.25 degrees Celsius, so that's pretty tightly clustered around 24.5 degrees, what would be the probability of getting a reading between 24.1 and 24.6? So quite a bit less than the mean and just a little bit over the mean. Well, to do that, we'd have to find the CDF values for each of those particular ones and then take the difference between them. So if we look for 24.6, that's the high end, mean of 24.5 and 0.25. So that's the probability that the value is less than 24.6. And then this is the probability that the value is less than 24.1. And if it's going to be in between 24.1 and 24.6, then it's going to be the probability for 24.6 minus the probability for 24.1. And when we do that calculation, we wind up with 60%. So about a 60% chance of getting into that range. Now once again down here, I can draw a picture for you that sorts all of that stuff out. And I can do the calculation and make the plot. So here I've got my function, norm CDF. I'm looking over a space between 23 and 26. I've got a mean of 24.5 and a standard deviation of 0.25, and I plot that out. There's that cumulative density function. And the mean is in here at 24.5. There's 50% of the probability is below the mean, 50% is above the mean. So that makes sense. And I can plot some lines on here the same way I did before. I'm going to plot a green line, and I'm using this color equal to G to be specific about the green I want. So I plot that green line, and I plot that red line. That's 24.1, and that's 24.6. And you can see that's about 64%, that's about 4% or something in that range. And so when you subtract the two, you get about that 60%. So graphically, this makes sense out of what we did numerically up here. Now, in the course textbook, Figliola and Beasley, or any other similar textbook, you'll find tables of these PDF and CDF curves. They're usually plotted in a half space. So plots of this integral here, and the orange line is what you'll see. So it'll start from 0 and go up to a half instead of starting from way over here at 0 and going up to 1 up there. So this is just the top half of this curve here. It's that part. And you'll find tables with a whole lot of numerical values in them. You're welcome to go and use those tables with numerical values in them if you really want to. I like graphs like this and numerical calculations like that way better than looking things up and trying to transcribe them out of tables of numbers. I did enough of that in thermodynamics. So use these functions to figure out what the probabilities are. And if you need a curve to be able to visualize what's going on, then this plot down here, made from this code here, gives you both the PDF on this axis over here that goes up to about 0.4, and the CDF, the cumulative density function, on this axis over here that goes up to 1. And this, of course, is for mean of 0 and standard deviation of 1, but you can transpose all of this for exactly the same characteristics that you would need for values that go with other means and standard deviations. So this is a Gaussian normal curve. You can generate it with this code, but more importantly, if you need to get answers from this curve, use the functions up here the way we've used them to answer these kinds of questions. We'll use these Gaussian curves not so much to get actual values out of them, but as an idea for when we're combining uncertainties for our measurements. So remember, one standard deviation out, we're looking at about 68% of the total space. 2 standard deviations out, we're looking at about 95% of the probability. And we'll use 2 standard deviations as our uncertainty value every time, because we're interested in knowing what is the uncertainty in our measurement with a region of 95% probability.